Great, thank you. Thanks, Lauren, for inviting me to give this talk here today. So yeah, today I'll be talking about recent work of mine regarding convergence of these ergodic averages along the sequence omega n. So first, just want to define what this sequence does. So omega of n, we're going to let denote the number of prime factors of n. Counted with multiplicities.
Sarah could run.
So for instance, this sequence takes value 1 infinitely often along the primes, value 2 along any product of 2 primes or a prime squared, and so on. And so this sequence has a lot of background coming from number theory, and I'll talk about a little bit of that later. But I've been studying this sequence from a pretty dynamical point of view, so I wanted to give an idea of that today. So we're talking mostly about Pointwise Ergodic theorems. So I just wanted to start first by stating the Birkhoff Ergodic theorem. Which says that given any measure preserving system, so here our systems are always going to be measure preserving. Should write this separately, but so X we're always going to take to be a compact metric space. Mu, a Borel probability measure. And T, a measure preserving transformation. And we're going to take it to be a homeomorphism. Okay, so that's our setting. And in this setting, Birkhoff's ergodic theorem says that given any measure preserving system and any L1 function, maybe I'll write this down here so people at the far side can see it. And the Birkhoff averages of F converge pointwise almost everywhere. So the reason why I'm taking the time to write down this theorem that I'm guessing most people here know is to really just emphasize that the iterates here are taken along the integers. And so it's been a question that's been studied over the past several decades in ergodic theory. What happens if we take these iterates coming from other sequences?
Can I ask you, you for convenience assume compactness and all this topology? Because Birkhoff is purely theoretical thing.
I know in my work, I think we do need T to be invertible, compact. We do use it for convenience. I haven't checked if you can generalize it from there, but yeah, for convenience mainly. I only did it in that setting.
Oh.
Yeah. All right. And so now we're going to start looking at what happens along other sequences. So first, a quick definition. The sequence is called universally good for LP. If for all measure preserving systems, and all LP functions, when we take these non-standard ergodic averages along AN, these averages converge pointwise almost everywhere.
It says for all x mu t. It's for all measure preserved systems. Oh, I didn't hear. I have to ask about t.
Yeah, is that a fixed P
Sorry,
or
question?
you're fixing P or? is it
I'm fixing, oh, so for all P,
For what?
wait, no, it's good for, yeah, LP, we're fixing P.
You're fixing.
It's good for LP, a fixed P, if this happens. All right, and so in this language, I'm gonna do a few examples. So in this language, what Birkhoff's ergodic theorem says is that the integers are good for LP when P is equal to 1. And we can extend this to say it's good for LP and any P greater than or equal to 1. But as stated, it would be equals 1. And the next sequence that I think people looked at was a set of perfect squares. This was shown by Bergelson. In 1988, that the set of squares is good for, or universally good for LP, and any LP space for P strictly greater than 1. Next example is the set of primes. This was also shown to be universally good for LP, for any P strictly greater than 1. This is the white girdle. Also 1988. And so in all of these cases, we do know that these sequences are universally good in these cases. So what about maybe here, the pesky case of what happens when P is equal to 1? In this case, it is known what happens. And in fact, it's known that they're universally bad for LP in this case. So we're going to call a sequence universally bad. For LP. For any non-atomic ergodic system, we can find some LP function where those averages don't converge. So exists some LP function where these averages don't converge. Converge on a set of positive measure. And so a couple quick examples, as I mentioned. So it is known that, so in the case of the squares, they're universally bad for P is equal to 1. That's by Buzolich and Molden in, I think, 2010. And then the primes also equals 1 with La Victoire in 2011. And so, as I sort of set up over there, we're going to be looking at the sequence omega n today, right? And so the main question is going to be, what about omega n? So what can we say about pointwise convergence when these iterates are taken along the sequence omega n? So this was a question that was previously studied under the conditions of unique ergodicity by Bergelson and Richter. In this case, we get an affirmative answer. This is Bergelson and Richter from 2020. So they say that the result says that if we take a uniquely ergodic system and f to be a continuous function, and the averages along omega n do converge, and in fact they converge to the integral of that. And in this case, it isn't a pointwise almost everywhere result. This is for every point in the space.
I think if you want like the almost everywhere, then it's the same methods of Bourgain should work. Like if you, this is like a much stronger, like if you just were interested in the almost true result, then the same methods that Bourgain has.
So I'm going to get to, I guess, the almost everywhere result in a bit. And it actually turns out not to hold in that case.
Not to the integral, but the convergence, almost true convergence to some, no?
Oh,
Oh, because you just need to know the exponential sum, I thought.
No, I mean, it's different, like continuous life is.
No, this is different. Not this, but like the n squared result and stuff like that.
You get L2 convergence from the spectral theorem. But not
But Bourgain, of course. But Bourgain's methods, they like the one he does for the n squared thing.
No, but Bourgain does it almost everywhere. But on the other hand,
That's what I'm saying.
true, but at the same time, it's not the same situation, not analogous situation, because in uniquely ergodic case,
I know. That's what I
Bourgain
was
fails, so
saying.
it's different life.
I was exactly saying that. I was just saying that if you're interested in the result that's similar to Bourgain's result for squares, then the methods he used, the minute you want, he used, of course, for the spec. Never mind, later.
In any case, she will tell you.
Okay, so yeah, I am going to talk about
That's actually not the case.
I missed it.
So maybe we'll get there once I
Doesn't matter.
state the main
Yeah.
theorem.
Wait, but is it not the case even if he is greater than one?
It's greater than one. Yeah, let me also get to stating the theorem and then we can maybe discuss it a bit more. Okay. So yeah, I am going to take a short detour away from this stuff, but we will get back to it in like just a second. So as I mentioned before, there is a big background coming from number theory, and I wanted to just discuss that for a few minutes to show maybe more of the intuition about why we're looking specifically at the sequence omega n. And so it turns out that Bergelson and Richter's theorem simultaneously generalizes a lot of results coming from multiplicative number theory, talking about the asymptotic distribution of omega n. Okay. And so, for instance, Richter's theorem. Generalizes first the prime number theorem. So the prime number theorem, we're going to think of in one of its alternate formulations. The prime number theorem is equivalent to the statement that if we let lambda n denote the classical Liouville function, minus 1 to the power omega n. And the averages of the Liouville function tend to 0. And so in this formulation, which isn't dynamical yet, but is maybe more a little dynamically leaning because it's talking about averages of some function. From here, the key point is to see that the Liouville function can actually be captured by a uniquely ergodic system. So that gives us the tie to the Bergelson and Richter theorem. And so you can check, I won't write out all the details, that if you take x mu t to be rotational in 2 points, then you can write the Liouville function by choosing some appropriate continuous function. You can write the Liouville function in this way. And since this is uniquely ergodic, you can apply the Bergelson and Richter theorem. So then second, apply Selberg theorem. Which says that for all integers m and r the set of remainders, we look at this set of n, for which omega n is equivalent to r mod m. This set has density, natural density 1 over m. And third, Bergelson and Richter also generalizes the Ergodic theorem. Which says that for all irrational alpha, the sequence omega n alpha is uniformly distributed. 1, 1. So I won't write out any details, even like I did for the prime number theorem, but the idea is the same in this case. In order to apply the Bergelson and Richter theorem, you write it in some appropriate dynamically inspired way, and then find a uniquely ergodic system which captures that sequence. So in this case, turns out to be a rotation on m points, and here you take rotation on the torus by alpha. Okay. And so, yeah, this is just a short detour to say that even though we're looking at this stuff within this dynamical perspective, Bergelson and Richter's theorem is also interesting if you're looking at it from the number theoretic point of view, because it does simultaneously generalize a lot of these very interesting number theoretic results. But back to the ergodic theory and to some of the questions that were asked earlier. So Bergelson and Richter's theorem really does heavily rely on both the condition of unique ergodicity and the continuity of the function. Both of those are used pretty heavily in the proof. And so the question is, maybe what happens when we start changing these conditions? Okay. So let's say we asked about pointwise almost everywhere convergence in L1. And then relaxing to just ergodic systems. And so, short answer. This was recent work of mine to show that the answer here is actually no, convergence does not hold. And that in fact, omega n is universally bad.
What about p greater than 1?
So in p greater than 1, I think it's also going to be universally bad for a reason that I'll state the theorem slightly differently. It'll probably show what I mean.
But on probability space, that for L1, it will be bigger than.
No, it's like
No,
I'm
It's
in
the other
way around,
it's the other way. Yeah.
No, sorry,
Yeah,
sorry.
okay.
But you'll be on infinity. And then it will close.
Yeah.
That will be with L infinity.
As
Yes.
far as I remember Gauguin's argument for n squared, all you need to know is this omega and alpha and this distribution for p greater than 1. That's why I was asking.
No,
Yeah.
I think it's good topic for discussion.
Yeah,
See how it's-
yeah. No, that's why I was asking p greater than 1.
Yeah, I don't know about the Organ's argument, so I. All right, so yeah, I did state it here just for L1. The actual statement of the theorem is even more general than that. Myself. 2021. So we're going to be in a situation for the universally bound sequences. So we're going to take XT to be any non-atomic ergodic system. And we actually get a dense G delta subset R of the Borel sigma algebra. So let me stick that in there. Such that for any set coming from our dense G delta, if we look at our averages of the indicator function of the set A along omega n, take the lim sup. This is equal to 1. And if we look at the same for the lim in, this is equal to 0. And this happens almost everywhere. This is actually happening on a set of measurable. And so here, yeah, these indicator functions, these are LP for any P, they're all infinity. And so I think that this does go over into any LP space. All right. So a couple of remarks I want to make about this theorem. So first is how this still coincides with the Bergelson and Richter's theorem, okay? Because this theorem does still hold for uniquely ergodic systems. And so what this says, in order to coexist with Bergelson and Richter's theorem, is that the convergence, the counterexample to the convergence has to be coming from something that's L1 but not continuous. So uniquely ergodic systems this means the counterexample. I mean, we can see that it's coming from such a function. So it comes from something outside the set of continuous functions. Okay, so this means that for their theorem, it was really important that they considered both unique ergodicity and continuity of the function in their hypotheses. And then second, just wanted to remark that the statement that I've shown up here, this property has a name. So I want to write that. Yeah. So operators, so we'll consider these as averaging operators for a second. And in this case, you know that the averaging operators along omega n are said to have the strong sweeping out property. The strong sweeping out property. So if you don't know this term, it's maybe okay if you forget it, but I did want to point out that this is a property that's been studied both, it's coming from functional analysis, but recently has worked its way into ergodic theory in situations like this. And so this is giving another example of a sequence that has the strong sweeping out property. So for the next maybe 15, maybe 20 minutes, I'm going to get into the main ideas of the proof of this theorem. Are there any questions before we get started on that? Sketch of proof. The first thing that we want to do is essentially just to regroup our averages in a more useful way. When we're looking at these averages along omega n, it's maybe initially unclear how to handle this omega n hanging out in the iterates. I mean, that's the whole question. Okay. And so first, we're just going to rearrange the terms of this sum and write it instead in the following way. Okay, so we're going to regroup the terms in the following way. I'm just going to group them all up by the value of omega n. So now when we look at the sum, it's happening just along the integers in terms of the iterates. Okay. And so now we have some finite sum weighted by these values here. And luckily for us, terms like this have been well studied in number theory. And so we're going to start to apply some more number theoretic tools here. So the main idea so we're going to obtain weight functions W sub n. They're going to be supported on large intervals I sub n. Such that, let's call this right hand side star is equal to now the sum over this finite interval weighted by our functions W. Up to some error that's like some constant times epsilon. Okay. And so as I've written it, it maybe doesn't look like I've done very much at this point. I've just replaced a finite weighted sum by another finite weighted sum. But the idea here is that the intervals and the weight functions that we get out of this approximation are going to give us a lot more control over what's happening. In particular, the size and shape of the intervals is going to give us a lot of information. And I'm not going to go through the precise construction of these weight functions. Rather, I just wanted to give a theorem that I think gives a lot of intuition for where they're coming from. This is coming from the Ergodic theorem, which states that for real numbers a less than b, if we look at the following averages, so we're going to take the indicator function of the interval ab, that is quantity omega n log n squared. converges to a Gaussian distribution. And so the left-hand side here, all this is doing is counting how many times does this value land within the interval between A and B, and it's saying that that is converging to this Gaussian distribution. Okay. So maybe in words, this means that for large n, we look at the first n terms of the sequence omega n. This is approaching a normal distribution. With mean and variance log n. And so the idea, I guess I didn't write on this board. So the idea is that the weight functions that we obtain have the same, follow the same principle. So our weight functions, Wn of k, are going to be Gaussian functions with mean and variance log n. Following. And the intervals are going to be also exactly the same as the ones appearing in the Erdős-Katz theorem. Right, so here I didn't really write it as looking like intervals, because this is counting for which n is omega n land in this interval centered around log n. Plus or minus some constants in the square root of log n. And then the idea is that we're going to choose this constant large enough so that it's capturing most of our distribution, and the terms that are left are negligible.
So in other words, the larger I make the C, the smaller I can make the epsilon, right?
Yeah. Yeah, the C is depending on the epsilon. So we're choosing C big enough such that all the terms that are falling outside of our interval are just getting captured in the error term over there. Okay, and so now that we've translated our original ergodic averages into these weighted sums, we can follow sort of a standard argument that was originally due to Rosenblatt and Birnel, which uses the following technique. First, we'll apply the Rochlin lemma. And okay, different epsilon here. We're going to use the Rochlin lemma to construct a set B, measurable set B, such that the following two properties hold. got the measure of B to be very small, less than epsilon. And we're gonna take some space. We look at the measure of the set of points. M. Look at the measure of the set of points such that the supremum. First, I'm just going to write this down and then I'll explain sort of how to think about it. Of the sum of our weight functions. All right, so we need the following two properties. The set is small, and then this. How do we think about that property? We'll just use.
Excuse me, do you take supremum over n or k? Over n, right?
Taking the supremum over all the k that are bigger than this fixed m.
But then k, this is the index of summation.
Oh, did I miss it? Okay, probably messed up my indices here. This is supposed to be the n, the n showing up there. Thank you. Yeah. Okay. And so I just want to draw a small picture for this. So breaking down what this condition means, right? So this is just counting here. We're just looking at our weighted sums. This is just counting if we're looking only at the piece of the orbit lying in this interval in, how often are we falling in the set B? Okay. And then we weight by our weight functions. And then we take the supremum over all n. So here's where I want to draw a small picture. So we're going to have some interval I sub m from our fixed m here. And the idea is that these intervals are drifting out to infinity with n. Okay. And so what this says is that no matter, let's see, yeah, no matter how large we choose m, we can always find some later interval I sub n, such that most of the points on this orbit lying in this interval I sub n are landing in B. And then lastly, the set of points for which that condition holds is also very large. And so such a condition seems strange that we're getting this very small set where most of the time we're landing in this small set B. If that feels weird for pointwise convergence, it probably should, because we're trying to show pointwise convergence doesn't hold. And so the last step of the proof leave the statement up there. It's actually just a variant of the Banach principle. Which guarantees our density delta that we wanted. All right, so we take the limb soup. Of our weighted sums. We get 1. And then take the limb in. We get 0, and this happens almost everywhere.
So can you remind me what the Banach principle is?
So it's a very generally stated and complicated. Yeah, I don't think it's worth writing on the board. But basically it says that in the case of the averaging operators, I mean, it says exactly this. So if we have averaging operators that satisfy these two properties here, you can find a set that is small that satisfies this property, then we're automatically guaranteed the density delta that satisfies those two conditions. And I guess the idea behind, maybe I'll make a note. We just want an idea of why it's true. It's maybe not super interesting, but yeah, I find the proof of it actually a little unenlightening. But so you define these sets. Which is basically all of the sets, all the measurable sets, where this condition doesn't hold. So where we're getting that the supremum is less than 1 minus epsilon. Maybe we won't write that all out. Use these assumptions to show that this is a meager set, take some countable union of them, and it'll automatically guarantee this condition. You do the same thing for all the things whose complement lie in that set, and you get the limit condition. So yeah, I do find it a little maybe underwhelming from the dynamical point of view, because it just comes down to some topological argument. Yeah. Can I answer my question? Are there any more questions on the ideas of the proof of this theorem?
What What properties of W are you going to say it soon, or like what properties do you use of these weights?
Yeah, so really the important part isn't necessarily the exact, like, I mean, I never really use specifically that they are Gaussian distributions anywhere. I just use that they like integrate to 1. I think was the only.
So that's
But then
for
for
any
But then, so what the important part is really the shape of the intervals. Somehow that becomes more important than the actual weights. And so the idea is that, but this is basically saying that omega n is acting very similar to log n. Okay, and so that's what's important.
So I have, okay,
So these
maybe a
intervals are centered
rephrase.
pretty tightly around log n. That's what becomes important.
Okay,
So the actual shape of the weight functions was less important, but the location of where they're grouping up is the most important part.
So it's not enough that they kind of become disjoint, like run away to infinity?
I mean, this is also, I guess, sort of. Yeah, you do also need that somewhere.
But the log behavior is also important.
Yeah, the log n behavior is important, but they do also drift out to infinity. You need both of those things. Yeah.
But it's not important that it's log, right? It could be any other function that goes into
If it was n squared,
you can call it
so
different.
as long as they are disjoint.
Yeah, as long as it goes to infinity and
Okay,
it
that's
accumulates
fine.
around there.
but
That's
then
my
that doesn't
understanding.
happen to these like weights of these almost primes. They don't satisfy the same. Would they not act in the same way somehow? Because otherwise, I'm still stuck. Sorry, on the speed question on this, because you know, if the result is true for p greater than 1, that's more striking, right? Because it's you give a counterexample for p equals 1, then it's already known for the primes. Then you would think that okay, that they behave badly in the same way. But if it's also true for p greater than 1, that actually is a counterexample to this Bourgain type method. That's why I was asking that. So that's why I'm curious as to.
Are we already in discussion session? Maybe she has still things to say, because if during discussion. I
You're
would
cutting
like-
me off all the time, Vitali.
No, I would
I will
like
shut you off also. You should be aware.
Actually, I was trying to help the discussion by asking if we have discussion.
Yeah,
And when we will
discussion
have
is all the time, you
Let
know,
me-
it's,
Let me finish. When we will have discussion, I would like to add to this discussion, but I wonder if she still has to finish her talk. So it's not shutting you up, just waiting my
you're
line.
keeping me in suspense.
Yes, that's my goal.
That's the-
So, I mean, I guess I can answer. I'm not gonna say more about this stuff. I'm gonna move over to something different. So, yeah, I'm not gonna say more about this. Maybe we can, yeah, talk about it after.
Yeah, so can I ask a question about how you're using Berkelson on here? Should I think of this set B as like a,
Oh,
So
Roku's something,
you-
yeah.
is it, you take some Rockland tower and you take like a very thin vertical strip of the tower or?
So basically, you're gonna take like the top chunk of the Rockland Tower.
Oh, the top.
Yeah. You're gonna take some very large Rockland Tower. It's gonna go up to like log n. You're basically taking the chunk that's coming from the interval. Take up to this iterate, and then you take the top piece, will eventually be the b, you take like n large enough.
That's small because log n is small. The size of the tower.
Yeah, it becomes small because this is the size like some constant square root log n compared to, yeah.
Right, if you go along the primes to the squares, you'll have stuff in all levels of the tower.
And
And here you kind of only
Yeah.
find stuff in the very end of the tower. And that's maybe the main difference.
okay,
Maybe.
yeah, I don't know.
When we'll be having discussion,
No.
I will have, but I don't want to destroy her talk. She still has things to say. So it's premature to have this discussion, but I really have something interesting to say. I just want to wait. Let her finish the talk. And then we'll talk.
Yeah, I do want to at least the statement of the other theorem, but that is from a very different direction from this one. Yeah, so that is sort of the end of the proof of and the discussion of this pointwise result. Do you want to talk about a result that's in a slightly different direction, also related to Bergelson and Richter's theorem? Right, so we've talked about two very different behaviors of omega n at this point. One coming from the prime number theorem. So, yes, behaviors of omega n. The prime number theorem we thought of in its reformulation, which says that the averages of the Liouville function tend to 0. And so we can think of this again as saying that omega n is even asymptotically exactly half the time. So, omega n is even half of the time. So again, speaking asymptotically. And then second, we have the behavior coming from the Erdős-Kac theorem. This is a very different behavior of omega n, which was counting the n for which omega n lands in intervals of this type. So the Erdős-Kac theorem tells us that within such intervals, omega n becomes roughly normally distributed, right? With mean, yeah. Oh, I just erased it. And so then the question is how these two behaviors correlate with each other, or if they don't. And so for instance, maybe if we're looking in these intervals and we only want to consider which values of those are even, maybe they would be clumping up in certain spaces, or maybe there's somehow too many of them that are even. And we'd be getting some correlation between these two behaviors. So it's another result of mine. Not yet. To show that behaviors like this can't happen. So first I need to do a definition before stating the theorem. two sequences. And then I'm going to call asymptotically uncorrelated. If, when we look at their correlations, this is tending to the product of the two individual averages. Some error, little O of 1. And so then the statement of the theorem says that if we look at the Liouville function, which is capturing this behavior about the parity of omega n, and I had just erased it, but this was the sequence capturing the behavior coming from the Ergodic theorem, which talks about when omega falls in these intervals centered around log n. These two sequences are asymptotically uncorrelated. And so now if we were to interpret this from a number theoretic point of view, this is telling us that if we were to look at so large values of n, if we look at the first n in terms of the sequence omega n, and we only restrict ourselves the values which are even, then this still approaches a normal distribution with mean and variance log n. We don't actually get any situations where maybe the even values are somehow distributing differently within such intervals. They're still following this same normal distribution. Okay, yeah, that was all I wanted to say. Yeah, are there any questions?
Questions for me?
So your second result, I guess, and the Bergelson and Richter theorem. This also works for little omega.
This one also works for little omega. I expect this one to also, but haven't actually checked. But I expect it would.
So in other words, your sweeping out property should work for small omega, right? So you indicated it here, but it's in the core.
In this theorem over here.
Yeah.
I mean, this whole
I mean, I
argument
just
you
haven't
gave,
looked at it.
like the whole argument you gave to prove that, like
Yeah, again, I would expect it to still hold, but I just.
like the Ergodic cats theorem still holds for little omega. So
Should be.
And they surprisingly, they oscillate the same way. They sum up the same way. So and in our theorem, it is working. So it should be.
Yeah, I would expect it to. I just, yeah, haven't actually checked.
Can I ask a simple one? Have you checked, these are the typical fields corrected if you use logarithmic coverage or double logarithm? Have you
I
tried?
remember looking at it. I don't think I ever found an answer whether
So it
like
was not
in
trivial.
this case, if maybe it does somehow hold for logarithmic. I haven't.
So for log, you will still expect, because if the principle is, for example, if it was just log n, you will have to take double logarithm to fix it, and perhaps, but it's not log n. An easier way to, so if you put irrational weights, have you tried this? E to the n alpha?
No, I haven't tried
This
sticking
I
in
would
other
expect that it goes there.
Yeah.
But okay. I see.
Your weight sometimes may create independence.
The weight system is this. So if you put weight -1 to the n, this is how it does.
To be enough for price.
Yeah, but without the false.
She created localized discussion.
For the pointwise ergodic theorem.
Yeah, so this last result, is it also if you replace instead of lambda, if you take like sequences coming from the theorem?
Yeah, so I didn't state it, but yeah, Bergelson and Richter theorem generalizes the prime number theorem, and in the same way, we can stick in there instead of the Liouville function, anything coming from a unique
So you take that same result, you throw on
Yep.
your checks, then you guys kind of.
Yep, so you take the same thing, and instead of the Liouville function, you stick in these T omega and X, then yeah, you're still good. Coming from a unique ergodic system and a continuous function.
I would
Yeah.
add, following your question, I think that any function, Lauren, that I have many functions satisfied. I think each of them will satisfy. And so, Tammy?
No, I'm just curious what fails in
No.
Ken's argument. No, I'm just.
To attract your attention because I want to say something clever related to your question originally. So, there is huge difference between Bourgain type positive and negative results and this difference. And that's what I want to explain what I think about. You see, Bourgain, when he proves along squares, or Mate, who proved along triangles, Bourgain later did it too, by the way. So it is monotonely growing sequence. So there's something crazy about its gaps. Gaps are relatively regular. And Mate, at some stage, he got a lot of intuition, which turned out to be wrong because he thought that any sequence with monotonically growing gaps will be bad for L1 and good for LP bigger than 1. It was beautiful conjecture. It didn't work because after work of Patrick Victoire, it was clear that along primes and squares, you will not have L1 pointwise, but for sequences growing like that, you may have L1.
Yeah, if you take, for instance, integer part of n to power c, when c is bigger than 1, very close, then you can have weak type 1.
For example.
I see.
And yet what we proved with Bourgain and Chernitz, and we showed that along n to power alpha, and that gets close, you see? So there is low level of good behavior that uniform distribution mod 1. There are thus many sequences, sometimes hard to get, sometimes not. By the way, this corollary from this result that omega 1 times alpha, which is Erdos-Delange, it's non-trivial theorem for them. Namely, when Erdos mentioned it in 46, he said it should be true, it is true, but it's non-trivial. Then Delange proved it in 58, it took 12 years, and heavyweight. We are lucky because we don't get any bounds or whatever, so it follows easily from this general result. So the first level, it's uniform distribution mod 1. You get this or that way, but you have results. For example, n to power alpha non-integer. Mod 1 is uniformly distributed. Next level is if it is good for unique ergodicity, intermediate level. As we see here, it is true.
Yeah.
But what Ronnie Pavlov showed that along squares in unique ergodicity case, it's already not. So unique ergodicity is already distinct from uniform distribution of 1. And then next level, even more, that's LP, L1, L infinity. And by the way, then there are many interesting counterexamples, and they all seem to get to this. For example, I don't remember if I ever checked, but Marstrand has interesting counterexample to Hinching conjecture. When you take summation of nx mod 1. Because of uniform distribution, nx mod 1 is uniformly distributed for almost every x, indeed for all but countably many x's. That's why you have ergodic theorem along nx mod 1. Hinching conjecture that it's true almost everywhere. So it was killed by Marstrand. And I think if you check Marstrand, it will be again a uniform sweeping out property. This seems to be really the feature of this. But one more remark. Why? So where is the subtle distinction? One thing is uniform distribution and growing gaps. Then forget even about unique ergodicity. Here we are lucky because omega of n is oscillating but takes a lot of values. So it's totally new phenomenon which I don't feel strongly. I don't understand it. But because omega of n is oscillating and yet taking all the values, you have even unique ergodicity. But as Kaitlyn shows, forget about L1 or L infinity. So these are amazingly interesting phenomena, but back to distinction. There are distinctions, and the Bourgain is one thing, and this is another.
Yeah, okay. Cool.
Any other questions? Okay, let's thank Katie again.